In this video, we're going to be looking at a variation on the standard molar solubility calculation type of problem. So in this case, because we're dealing with the dissociation of silver phosphate, we can go ahead and write the KSP value like so, which is the concentration of silver ions cubed, corresponding to the coefficient of 3, times the concentration of phosphate ions here. Where this gets complicated is the fact that we have a small concentration of silver nitrate that is already in the solution before we want to try dissolving silver phosphate into this solution here. So if we consider silver nitrate, which looks like a fairly unspectacular compound, because again, all nitrates are soluble, that means that 100% of this compound is going to dissociate into separate silver and nitrate ions like this. And if we know what the concentration of silver nitrate is, 0.20 moles per liter, and we know that the mole ratio between silver nitrate and silver is 1:1, we are going to have the same concentration of silver as silver nitrate. Now, what does this mean for our solution or our dissociation of silver phosphate? Well, it means that because this silver nitrate was here before we tried this dissociation, that means that unlike phosphate, where we still do not have any phosphate within this solution, we actually have a small amount of silver ions that are already dissolved within the solution. Before we even start calculations, we can make a prediction of what this is going to do to molar solubility. Remember, of course, that solubility equilibrium occurs when we have reached the saturation point. That is, when we can no longer dissolve any solute within a specific volume of solvent. Now, because we already have a small amount of silver within this solution here, that means that we are closer to hitting our saturation point. And if we're closer to hitting the saturation point, it means that likely we are going to be able to dissolve less solute within our solvent. So let's do the calculation in order to see whether this is true. We can start off by treating this as a normal molar solubility problem by calculating what the change magnitude and direction is. So because we don't have any phosphate, we cannot do the precipitation reaction, which means the equilibrium has to move in the direction of the dissociation reaction. And because of the mole ratios, we know that our change is going to be plus 3x for silver and plus x for phosphate. So even though we would have x moles per liter of phosphate, and because the moles of phosphate and moles of silver phosphate are the same, x is also equal to our molar solubility of silver phosphate. The problem is with the equilibrium concentration of silver, and because our initial measurement is not 0, we're going to have 0.20 moles per liter plus 3x as our initial concentration of silver, and we can see what the problem with calculating this is when we put this into our KSP formula. So if we compare this, so 1.1 times 10 to the negative 16 is our equilibrium constant, and then our concentration of silver is 0.20 plus 3x cubed times x. Now, what this means is that we're going to get a fairly messy polynomial here, and if you keep track of the amount of x that we have, we're going to end up with a quartic function here, which means that we can't use the quadratic formula to solve it, and the only way to reasonably solve for x in a complicated situation like this is to actually just use a graphing calculator or graphing app and find out what x is by graphing it. However, we don't even actually need to do that, because if we consider what KSP represents and the fact that KSP's magnitude is very, 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 very small, if KSP is very small, that means that the magnitude of x, the magnitude of the change, which is based on KSP, is also going to be very small as well. The assumption that we can make is if the total percent dissociation, and to give you an idea of what this means, the percent dissociation of a solubility reaction is if we take the moles of solute that dissociates or simply dissolves and divide by the total moles of solute, the total number of moles of the undissolved solute that we add to our solution, and then express this as a percentage here. That is what the percent dissociation is, and because KSP is a very, very small number, this is going to be minuscule. And the general assumption is that as long as our percent dissociation is less than 10% of the original solute, we can therefore ignore what this X term is. So what this assumption is saying is because the magnitude of KSP is very, 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 very small, any change that we make to an original concentration is not going to have a significant effect on the original total, which means effectively that our initial concentration of silver, 0.20 moles per liter, is approximately equal to the original concentration plus the change due to the equilibrium shift, and therefore we can ignore this number entirely, which simplifies the calculation. We can't do this with phosphate because any increase will be an infinite increase over an initial concentration of 0, and mathematically we don't really need to either. So if we rewrite this without this slight change here, we would have our KSP value as equal to 0.20 cubed times x, and all we would need to do is, to isolate x, is divide both sides by 0.20 cubed. And if you put this into your calculator, you will end up with, exactly 1.375 times 10 to the negative 14 moles per liter, which we can then round to two significant digits to match our KSP of 1.4 times 10 to the negative 14 moles per liter of our solute silver phosphate. So what we can see here is that this is a minuscule number. Basically, nothing dissolves because of this original concentration of silver that is already present within the solution before we try to dissolve any more. In the next series of videos, we're going to be applying our knowledge of Le Chatelier's principle in order to understand why the solubility of a given solute decreases if we already have a small concentration of one of the ions present within solution.